So, yesterday we looked at long division, and I said that we're going to learn today about synthetic division, which is a different way to divide a polynomial by a binomial. It's a quicker, easier, much more compact way of doing it. So again, it's a method of performing polynomial long division involving a binomial divisor that uses only the coefficients of the terms and fewer calculations. So let's start by doing this division first by long division, and then we'll make some connections to see how synthetic division works. So x plus 2 is being divided into that polynomial. A quick check, we see that it's in the right order, meaning descending order of power, and there are no terms missing. Remember, if there's any terms missing, if there was an x squared missing, we'd have to include that with the 0x squared. Okay, Adil? Yeah, I knew you knew. I knew. So again, we need to put something on top here, and whatever we put on top, we're going to multiply by what's in front, but we need a positive x cubed down below so that when we subtract, they cancel. And that's how we know that we need to put an x squared up top. Whatever goes on top, again, gets multiplied by what's in front. The x squared times the x gives us our x cubed, but also the x squared times the 2 is positive 2x squared, and then we subtract. We subtract, and the x cubes cancel. 4x squared, take away 2x squared, leaves us with 2x squared, and we bring down that next term of positive x. So again, we need to add another term on the top, and whatever we put on top, we need to multiply by what's in front, but we must have a 2x squared here so that when we subtract, they cancel, and that's how we know we need a positive 2x on top now. Multiply that by the x in front, gives us our 2x squared as well. The 2x is multiplied by the 2, it gives plus 4x, and then we subtract. So when we subtract, the 2x squareds cancel. You'll have x take away 4x, which is negative 3x, and we bring down that last term, which is the minus 6. And we need a negative 3 on top here, so that when we multiply by what's in front, we'll also get negative 3x, and we'll also get negative 6. And remember, we're subtracting here, and in each case, the minus minus becomes a plus positive. They're both going to cancel, and we get a remainder of 0. So that is the answer. X squared plus 2x minus 3. Because we get a remainder of 0, this tells us that x plus 2 divides evenly into p at x. Because we get a remainder of 0, it means that it divides evenly into p at x. So that is long division. We did that yesterday. So now let's see how synthetic division works. As it said above, synthetic division only involves the coefficients. So in this case here, if we're going to do this using synthetic division, we would say that we're dividing plus 2, that stands for x plus 2 because it only involves coefficients, into, the other thing that's different here is that we don't actually use the division symbol, it's just a line to divide the divisor and the dividend. But that's being divided into 1x cubed plus 4x squared plus 1x minus 6. It involves only the coefficients, none of the variables. So this is how you would set up that division using synthetic division. So there's lots of differences. The first being that there's no variables in here at all. It just involves the coefficients. Secondly, when we did it with long division, the answer is at the top. With synthetic division, we're going to get the coefficients for the answer at the bottom, but we need to leave a space here because we're going to put some numbers above that line, but the numbers on the bottom will be the coefficients of the answer. If we look back at what we did with long division, the initial term coefficient of the dividend was 1, and that is also the initial term coefficient of the quotient, the answer. That will always happen. Whatever the initial term coefficient is of the dividend, that will equal the initial term coefficient of the quotient, the answer. And we could look back at all the examples we did yesterday and you would see that happening. Whatever that first coefficient is, that'll be the first coefficient in the answer, which means whatever this first coefficient is, we can automatically copy it down the bottom. The initial term coefficients of the dividend and the quotient are always the same. Now, again, these numbers at the bottom represent the coefficients for the answer, the quotient. When we got our terms for our quotient on top, the next thing we did is we multiplied by what's in front. So we're going to do the same thing here. This one on the bottom is the initial term of the quotient. You're going to multiply by what's in front. 1 times 2 is plus 2. And then you subtract. 4 minus 2 is plus 2. Notice those two terms on the bottom match the first two coefficients on the top when we did it long division. So this number 2 again gets multiplied by what's in front. 2 times 2 is plus 4. And we subtract. 1 take away 4 is negative 3. That negative 3 matches the last term in the quotient. But we're not done yet because we have to get a remainder, so we do it one more time. Negative 3 times 2 is negative 6. And remember, you're subtracting. Right? In each case, you're subtracting here. Negative 6, take away negative 6. The minus minus becomes a plus positive. So it actually becomes negative 6 plus 6, which is 0. That last number is our remainder. So I always put a box around it. And those three numbers in front represent the coefficients of the answer. In this case, we divided a third degree polynomial by a first degree. We divided an x cubed by an x. That'll give us an x squared. That's the degree of the answer. It's 1x squared plus 2x minus 3. There's synthetic division. Much simpler, much shorter. It only involves the coefficients. It does not involve any variables. Now, before we go on, I'm going to show you an alternate way to do this using synthetic instead of synthetic division. Okay? Sometimes mistakes are going to happen because you're subtracting, and sometimes you forget about the signs, whether it's a minus minus or a negative minus a positive. Often that's where the mistakes are going to occur. So if we could change this to adding instead of subtracting, that would certainly make life a little bit easier. And we can change it to adding as we go along instead of subtracting. All we have to do is say instead of dividing by x plus 2, we're going to divide by x minus 2. X minus 2 into 1x cubed plus 4x squared plus 1 take away 6. If we change it to an x minus 2 instead of an x plus 2, this will now allow us to add as we're going along instead of subtract, which is easier. So 1 times negative 2 is negative 2, and remember now we are adding. 4 plus negative 2 is positive 2. We get the same two first coefficients as we have above. Whatever numbers are written down below are multiplied by what's in front. 2 times negative 2 is negative 4, and we add. 1 plus negative 4 is negative 3. Again, the same three numbers that we had above. And then negative 2 times negative 3 is positive 6, and when you add, you still get a 0 remainder. So by changing the x plus 2 to an x minus 2, it allows us to add as we're going through, which is a little bit easier. Okay, so there we go. This is how we do synthetic division. So on the next page, we need to use synthetic division to divide, and then it says is check using long division. Well, remember yesterday we also saw a different way we could check. We could write that division statement and then check it that way. It doesn't really matter which way you check as long as you check. So instead of dividing by x plus 3, I'm going to change it to x minus 3 so I can add as I'm going along. And that's being divided into 2x cubed plus 3x squared minus 4x plus 15. They're in the right order. There's no terms missing. We leave a space and write down that initial term coefficient, because the initial term coefficient in the dividend will equal the initial term coefficient in the quotient, the answer. And then you multiply and add. 2 times negative 3 is negative 6. When we add, we're going to get minus 3. Negative 3 times negative 3 is positive 9. When we add, we're going to get positive 5. And negative 3 times 5 is negative 15. When we add, we get a remainder of 0. The remainder is 0. So this means, again, that x plus 3 divides evenly into the polynomial. And once again, we divided a third degree polynomial by a first degree. An x cubed divided by an x gives us an x squared. So if we write our division statement here, 2x cubed plus 3x squared minus 4x plus 15 divided by x plus 3 gives us our quotient, our answer, which would be 2x squared minus 3x plus 5 with the remainder of 0. So we don't need to put a plus 0 over x plus 3 there, like we did yesterday when we used our division statement, because the remainder is 0. So to check this one, we would need to multiply both sides by x plus 3. To get p at x by itself on the left side, they will cancel. And so we should get the same thing on the right side when we multiply this out. So multiply everything in the trinomial first by the x, and then by the 3. And when we simplify this, we've got our 2x cubed. Negative 3x squared plus 6x squared is positive 3x squared. That's the right second term. 5x take away 9x is negative 4x, and then plus 15. So there's our check. We just showed that our answer is correct. Just so there's no confusing here, this is our answer. The coefficients, or the numbers at the bottom, give us the coefficients of the answer. Right? So in this case here, instead of dividing by x minus 2, we'll divide by x plus 2. And again, we do this so that we can add as we're going along. Looking at p at x, it's written in the proper order of descending power. There's no terms missing, so you don't have to include any coefficients of 0. It goes into 1x cubed plus 7x squared minus 3x plus 4. Leave a space, draw your line. The first number is always copied down. And we change it from an x minus 2 to an x plus 2, so we can multiply now and add the numbers together. 1 times 2 is plus 2. 7 plus 2 is positive 9. 2 times 9 is positive 18. Negative 3 plus 18 is positive 15. 2 times 15 is plus 30. We add those together and we get positive 34. That is our remainder. So in this case, this tells us that x minus 2 does not divide evenly into p at x. Because if that were true, you'd have to get a 0 remainder. And we don't. It doesn't divide evenly into p at x. Right? We can still write our answer. Once again, we divided a third degree polynomial, an x cubed by an x. That gives us an x squared. It'll be 1x squared plus 9x plus 15 plus the remainder is 34, which is always written as a ratio involving the original divisor, x minus 2. This one didn't ask us to check, so we didn't write a complete division statement. and we're not asked to check it. But you could always check just to make sure. I've shown you how. So remember, we are leading towards factoring third and fourth degree polynomials. That's what we're working towards. And the factors give us the x-intercept. So it's going to help us with sketches of these polynomial functions. So the remainder theorem states that when a polynomial in x, p at x is divided by a binomial of the form x minus a, you can find the remainder by evaluating that polynomial for p at a. And why is knowing the remainder important? Well, we've been talking about that. If the remainder is 0, that means that the binomial divides evenly into the polynomial, which means that the binomial is one of the factors of the polynomial. If it divides evenly, it's a factor. And if it divides evenly, that is because the remainder is 0. Right? So if we can find some values of a such that the remainder is 0, it helps us find our first factor. And so this is what the remainder theorem could be used for. You can find the remainder when you divide a polynomial by a binomial x minus a by evaluating that polynomial for p at a. So use the remainder theorem to determine the remainder when p at x is divided by x plus 4, and then we will divide or verify it by synthetic division. So we're going to divide x cubed minus 10x plus 6 by x plus 4. Now, remainder theorem says you can find the remainder when a polynomial is divided by a binomial of the form x minus a. You can find the remainder by evaluating for p at a. So that's where we need to start. We need to figure out what value of a we need to use here. And so you always compare the binomial to the general expression x minus a. And you need to ask yourself, what number do you need to put in for a so that that expression becomes x plus 4? And the answer would be a needs to be negative 4, so that the minus minus becomes a plus positive, and you will get x plus 4. In this case here, the value of a is negative 4. So we need to find p at negative 4. What is the value of this polynomial when x is negative 4? So the negative 4 is cubed minus 10 times negative 4 plus 6. Negative 4 all cubed is negative 64 plus 40 plus 6. Negative 64 plus 40 is negative 24 plus 6 is negative 18. That's what p at negative 4 gives us. So again, that means that when you divide p at x by x plus 4, the remainder is going to be negative 18. It tells us that x plus 4 does not divide evenly into p at x. For that to happen, the remainder would need to be 0, but it's not. It also tells us then that x plus 4 is not a factor of p at x. And that's what we're working towards. We're trying to find the factors of a polynomial. So we want to verify our answer using synthetic division. So in this case here, we would change the x plus 4 to x minus 4. And also in this case, there is an x squared term missing. So I'm going to include that with a coefficient of 0. I got 1x cubed plus 0x squareds minus 10x's plus 6. There is no x squared in that p at x, so we need to include that with a coefficient of 0. And now we multiply and add. 1 times negative 4 is negative 4. We add and get negative 4. 0 plus negative 4 is negative 4. Negative 4 times negative 4 is positive 16. We add and get positive 6. Negative 10 plus 16 is positive 6. And then 6 times negative 4 is negative 24. We'll add those together and we'll get negative 18. That's our remainder. So it worked, right? P at negative 4 did give us the right remainder. We checked it with synthetic division. So in this case here, we want to divide negative 4x to the 4. So I'm just going to write it in the proper order. Notice there is no x cubed or x squared term here. So when we check with synthetic division, we're going to have to deal with that by putting in a 0 for the x cubed coefficient as well as a 0 for the x squared coefficient. And make sure that they're in the right order, which I just did. But first, we're going to use the remainder theorem to find out what the remainder is when you divide that polynomial by x minus 3. If you compare x minus 3 to x minus a, you should realize that our a value is 3. If you put a 3 in for a, you will get x minus 3. So now we need to find out what p at 3 is. Into 11 times 3 minus 4 times 3 to the 4th minus 7. 11 times 3 is 33, take away. Now 3 to the 4th is 81 times 4, 162, 324, I think. Better check that. 4 times 3 to the power 4. Yep. So obviously this is not going to be 0. It's negative 298. Again, this would be the remainder when we divide. So that tells us then that x minus 3 will not be a factor of p at x. In order for a binomial to be a factor, the remainder has to be 0. But just to make sure, we'll check that with synthetic division. We change the x minus 3 to x plus 3, and it's divided into negative 4x to the 4th. And again, we have to put a 0 there for the x cubed, another 0 for the x squared, a positive 11x, and a minus 7. Three times negative 4 is negative 12, and we add. 3 times negative 12 is negative 36, and we add. 3 times negative 36 is negative 108, I think. So I'll have negative 108 there. And when you add those together, you'll get negative 97. Negative 97 times 3, negative 291, I think. Yep. And when you add them, you'll get negative 298 as the remainder. So it checks. Again, because the remainder is not 0, that means that x minus 3 is not a factor of p at x. It does not divide evenly into that. Because if it did, the remainder would be 0, and it's not. So these next two examples are questions that are maybe a little more common on the diploma exam. Have to do some problem solving. Given that p at x is 2x cubed minus 3x squared plus 4x plus k, determine the value of k. And again, that word determine means you need to show your work. Determine the value of k if the remainder is negative 38 when p at x is divided by x plus 2. When you divide p at x by x plus 2, you're going to get a remainder of 38, which means if you compare x plus 2 to x minus a, you should look at that and realize that a would have to be negative 2. You'd have to put a negative 2 into this expression x minus a so that it became x plus 2. That's our a value. And again, the remainder is negative 38 when p at x is divided by x plus 2. If you use the remainder theorem, what that tells us is that p at negative 2 has to equal negative 38. Because the remainder theorem tells us when you divide a polynomial by x minus a, the remainder can be found by evaluating for p at a. We're told the remainder is negative 38 when p at x is divided by x plus 2. We've determined that the value of a then would be negative 2, which means that p at negative 2 must equal 38. When we let x equal negative 2 in this expression, the whole thing has to equal negative 38. This is how we solve for k. We let x equal negative 2 everywhere in the expression, and the whole thing will have to equal negative 38. So we can solve for k. Negative 2 cubed is negative 8 times 2 is negative 16. Negative 2 all squared is 4 times negative 3 is negative 12. Negative 8 plus k equals negative 38. Negative 16 take away 12 is negative 28. Take away another 8 would be negative 36. And then to get k by itself, you would add 36 to both sides. And there's our answer. That is our k value. K must equal negative 2. Now we can check this. Let's check it using synthetic division to make sure. So over here is our check. We're going to divide by x plus 2, but we'll change it to an x minus 2 so we can add as we're going along. And that's going to be divided into 2x cubed minus 3x squared plus 4x. And we found our k value to be minus 2, so that'll be the last term of the dividend. Whatever that initial term coefficient is, it gets automatically copied down to the bottom. And now we're going to multiply and add. 2 times negative 2 is negative 4. We'll add and get negative 7. Negative 7 times negative 2 is positive 14. We're going to add and get positive 18. Negative 2 times 18 is negative 36. We add those together and we get negative 38, the correct remainder. So we just checked. Our answer is correct. When k is negative 2, the remainder is negative 38 when we divide the polynomial by x plus 2. Okay? Example 6. When you divide the first polynomial by x minus 2, you'll get the same remainder when the second polynomial is divided by x plus 1. Each of those polynomials have a k in them. It could be any variable except x, because x is the variable in each polynomial. It's the independent variable in each polynomial. But because it's the same variable k in front of the x terms, and it doesn't even have to be in front of the x terms. That part doesn't matter. Well, actually, I think it does, because you're going to have to solve for x. So it will have to be in front of the same degree term. But we can do this once again using remainder theorem. So for the first scenario, if you divide by x minus 2, and if you compare that to x minus a, you should realize that the a value there is 2. The second one, when you compare it to x minus a, you should realize that the a value is negative 1. So therefore, we're told you're going to get the same remainder when you do these two divisions. So that tells us that p at 2 in the first equation will equal p at negative 1 in the second equation. So maybe we'll say p sub 1 of 2 equals p sub 2 of negative 1. Letting x equal 2 in the first equation will give us the same answer when we let x equal negative 1 in the second equation, because those are the values of a. So in the first equation, I'm going to let x equal 2. And that will equal what I get in the second equation when I let x equal -1. I need to solve for k. Again, the word says determine the value of k, so we need to show our work. 2 cubed is 8 times 2 is 16. Minus 2 squared is 4 times 3 is 12. That'll become plus 2k minus 5 equaling -1 all cubed is -1. -1 all squared is 1 times 4 minus 1k plus 16. So on the left, 16 take away 12 is 4. 4 minus 5 is -1, so 2k minus 1 will equal -1 plus 4 is 3, plus 16 is 19 minus k. And we need to solve for k. So we'll add k to both sides, which will give us 3k on the left. Add the 1 to both sides. That's not right. -1. Yeah, you're right. -1 plus 4 is 3. 3 plus 16 is 19. Oh, no, it's not. Because -1 squared is +1. Unless I forgot. You're right. -4. Thank you. That's supposed to be a -4. So this 19 is incorrect. -1 take away 4 is -5. And -5 plus 16 is +11. So now when you add 1 to both sides, you're going to get 12 over there. That's better. And k will equal 4 when you divide both sides by 3. So let's check this. We should get the same remainder when we do the division. By letting k equal 4, we should get the same remainder. So the first one, we would change the x minus 2 to an x plus 2. And that's being divided into 2, take away 3, plus 4. That's our k value. That would be the coefficient of the x term, minus 5. So 2 times 2 is plus 4, and we add. 1 times 2 is plus 2, and we add. 2 times 6 is plus 12, and we'll add, and we'll get positive 7. That's our remainder. So we should get the same remainder, when we do the second synthetic division. We're told the remainders have to be the same. So when we divide x minus 1 into the second polynomial, which is 1x cubed minus 4x squared. Again, our k value was positive 4 plus 16. We should get the same remainder of positive 7. 1 times -1 is -1. We add and get -5. -1 times -5 is plus 5. We add and get positive 9. 1 times -9 is -9. We add and we get positive 7. We get the same remainder, which we were told we were supposed to. So that proves that our k value is correct. Okay. So there's a little bit of a review of what we've talked about. Synthetic division, long division, division statements, checking it, as well as the remainder theorem. So on page 124, questions 4, 8, and 9, you can work on those. I will post the solutions to, actually, you know what? I'm going to collect this one for marks. So you're going to hand this one in. So I won't be posting the solutions on Google Classroom. You do them on a separate piece of paper so you can hand them in. Okay?